Good afternoon, everyone. Good afternoon. Thanks for joining the live. Good afternoon. You are welcome if you are just joining the live. I am greeting you all. We're about to get started. In today's live session, I just quickly want to revise something very important, and that is optics. Optics, okay? The study of light and light waves. Basically, we just do a quick revision on optics in this very live session. So let's quickly get started. In case you are just coming, this is me. My name is Kenneth, and then I am the owner of Physademy. And today we'll be doing a quick live session on a topic in physics, basically a branch of physics which you know to be optics. Okay, optics. Now, if you are just coming, I'll then join you to stay put till the end of the video or the lesson because basically I'll be talking about a whole lot regarding optics. So let's get started without wasting much time. Like I said, if you are just coming, you can just like and share with your friends who perhaps will need this video, this live session too, so they can get a better understanding of optics. Don't forget also to, let's say, ask questions if you have any in the comment section as we progress. So first of all, we'll start. What is optics basically? We are just revising what we should have already known. Optics is a branch of physics, okay? It's a branch of physics that basically deals, okay, that studies light, okay, light and its behavior. Light and its behavior. That is basically what optics is all about. We are basically going to be focusing on how light behaves when it passes through a certain medium, when it hits a surface, okay? How it behaves in different cases. So basically, that is what optics is devoted to, okay? And then basically, there are different branches of physics. You have optics, you have geometric, and the others. We'll be going straight because I basically want also just revise what is very, very much important. So I have an outline here that I'm basically working with, okay? Now we know that optics studies light, and this light can exist as a wave. We call it light waves, okay? Now when you say a wave, we have to know what wave is, okay, before we continue. So that if I'm using the term light wave as we progress, you will not be confused. A wave is a disturbance, okay, uh, that travels through a medium, okay. It travels through a medium, transferring energy energy with it. So basically we'll go by it. A wave, first of all, is a disturbance. Let's say a vibration. It travels through a medium. That means every wave, in most cases, requires a medium. Most waves require a medium for them to pass through. And then what does it do? It does not just travel without carrying anything. It carries what we know to be what? Energy. So it's a disturbance that travels through a medium and transfer or what? Take along energy with it as it progresses. That is basically what we call wave. So light itself is an example of a wave. Now, as light being a wave, it should have what they call properties of waves. Okay, light has the properties of wave because it's a wave itself. Now, there are basically 5 properties that every wave must have. Okay, let's see what we call properties of waves. We are just basically revising what we should know. Okay, what we should know before we get started. Now, first thing first, a wave must be capable of reflection. Every wave must be capable of being reflected. That is it. Okay, that is when it hits a surface at an angle, it should be capable of bouncing off that surface. It should not be absorbed totally by the surface. Okay, it should be reflected. All right. Now, another property is that every wave should have another property which we call refraction. Refraction. Now, this property is basically the ability of a wave to pass from one medium to another. And during the process of passing from one medium to another, there will be a change in direction, as well as a change in wavelength, and also a change in velocity. We will get back to this again. I want to just finish listing them out first before we progress. Next, every wave must have what is called, must be capable of interference, what we call superposition. This is what I mean. Capable of being superimposed on each other. If you are just joining the live, do it to signify in the comment section, and as we progress, if you've got any question, do it to let me know. So you can just go through what I have on the board. Let me just check my comment section just in case I have any. Hi, you're welcome. Thanks for joining the live. I'm glad to have you here. Outside at last, I can see you. If you are just new to the channel, do it to drop a follow. I will be glad to have you on this space too. All right, let's continue. After what do you call it? Sorry, this is interference. Okay, it was kind of a bit too fast. That was why I made a mistake here. Interference. Every wave must be capable of being interfered or superimposed on each other. Now, the fourth, which is also important, every wave must be capable of being diffracted. All right, each of them have their own explanation that we follow. For now, I'm just listing them. So we have reflection, refraction, interference, diffraction, and guess what the last one is, guys? It is polarization. That is, as a wave, you should be capable of being what? Polarized. A wave must be capable of being polarized. Now, guys, there's a whole lot to all this, so I won't want to just jump this and go to the next step. I have to explain this in details on this part of the board. I guess you are following, and I guess the class is getting interesting, okay? So let me just give a glance again, just in case we have some new persons. I'll just need to say hi to. All right, do it to share the live with your friend. We are getting going. Do it to share the live with your friend. Okay, I think somebody have a question. Okay, you need to flip the screen sideways. Do you mean this way? Is this okay by you guys? Huh? But I think that way is actually better. I don't know. It kind of puts the whole, what I call it, the whole board under view. All right. So I think this way is better. Okay. So I'm coming. Let me fix something. I'm coming. Just give me a couple of seconds, guys. All right. Let's see what we have. Okay, they said orientation is locked. I don't get orientation is locked. Flick device back. Hi, Maraj. I'm glad to have you on this space. All right, so let's just continue. I just hope this does not distort our movements, our activity for today. So let's continue. I don't know why this gives me some stress. I need to fix it before we continue. Just be patient with me, guys. I promise we will have a whole lot to do today. And then let's see. They said rotation is locked. Rotate device back. All right, let's continue. I think I'll need to move this thing backward then. If that's the case, let me just move it backward so that it will cover the whole screen. Is this okay, Barros? I think it's better off now. All right, I think this is better off. So we'll be continuing the class now without delay. This is better off. All right, let's continue. So now, basically, we have to know what each of them means. Reflection, refraction, interference, diffraction, and polarization. All right, we won't waste much time on that. Now let's see what reflection is all about. Okay, let's see what reflection is all about. Now, like I said, light is basically a wave. Okay, and a wave is a disturbance that travels through a medium, and as it's traveling through the medium, it's transferring energy with it. That is what a wave is, and there are properties every wave must possess. We said a wave must have reflection, must be capable of being reflected, what we call reflection. 2, a wave must be capable of being refracted, what we call refraction. Must be capable of interfering on another wave, or we say must be capable of being superimposed on each other, which we call interference. We said the next that a wave must be capable of being diffracted, okay, which we call diffraction. And lastly, a wave must be capable of being what? Polarized. So these are the characteristics of a wave we'll be talking about. Now, reflection basically, this is how it works. Assuming this is a mirror surface, okay, a plane mirror. Let's be specific. Assuming this is a plane mirror, okay, a plane mirror. And then what happens was that light rays appears to be coming from this direction and, becoming incident on this plane mirror. What do you think will happen? Since we have agreed that light is a wave, what do you think will happen? Let me see in the comment section. And let me also check if we have new friends and all that. Alright, let's see what will happen as we progress. Because light is a wave, when it is incident on a surface, we call this incident ray. Take note, it is called incident ray. Okay? Now, because this light ray is a wave, because of the first property of a wave, which we call reflection, what will happen is that it will kind of bounce off the surface. Are you seeing that? Are you seeing that? It will bounce off the surface. Okay? This will now be the what? Reflected ray. You don't need to cram much. It's just based on how things work on its own. Light wave is coming from this direction. It gets incident on this plane mirror surface, and then it will what? Bounce off the surface. Okay? Now, I must also tell you some facts here. It is not all of the energy that was impendent on this surface that gets reflected. Some of them will be what? Absorbed. So incident ray, okay, let's just say incident energy will be equals to reflected energy, because we are talking in terms of the energy the rays is carrying. We are talking in terms of the energy that the light wave is carrying. It will be equal to reflected energy added to the energy that was absorbed. So let's take note of this. It is not just going to be I equals R. This is what actually happens to the energy. Some part of it will get absorbed. I hope that is clear to us. And I hope we are okay with this. We are kind of okay with the screen now. Alright? So let's progress. Let's progress. No time to waste. So this is what happens at a plane mirror surface when light ray is impedant on it. Now observe something. There is a vertical line that acts downward. The line is an imaginary line. It is not a real line. We usually draw it when we are doing optics diagram calculations and all that. This vertical line, we call it the normal. We call it the normal. Normal. That is it. Okay? Like saying normal to the plane surface. Because it is normal to this surface, you can notice it's acting perpendicularly to the surface. Mind you, it is imaginary. That's why I write it that's why I wrote it as a set of dotted lines. It does not really exist. Alright? Now this line is going to help us to know something. When this incident ray acts on this surface, if you observe something, it's actually making an angle with the imaginary normal. True or false? True, is it not? Now that angle, we call it theta I. Let's just say theta I better off. Okay? This theta I, it has a meaning. Okay? because the angle is between the normal, let's call it capital N, and the incident ray, it is called theta I. And what does theta I stand for? Incident angle. Okay? Incident angle, or you say angle of incidence. It's not hard, it's very, very easy. I hope we are following. Let me check if anybody has got any question so that I won't be sliding that. We will progress right now. Now this light ray, after it has hit the surface, we notice that most part of it will bounce off the surface, okay, as the reflected ray. Now observe something. This reflected ray is still going to make an angle with the imaginary normal, okay? In this case, or this time around, we call it theta arrow. Theta arrow, okay? The angle between the reflected ray and the normal, theta arrow. And what does that stand for? You can actually guess it. Reflected angle. That's very correct. Reflected angle. Or like I said for this guy, angle of reflection. Okay? Now that is for that. It's very, very easy. Now in most cases, sometimes they can just simply call it I. This one, they can just simply call it small arrow. It's still the same thing we are talking about. So perhaps when I'm solving questions, you now notice I did not use it as theta I. I just simply put I. I am still talking about the same thing. I am not contradicting myself. I hope we basically understand this up to this very point. Alright, let me just check. If you understand, let me know. So we progress. I don't want to leave anything unturned. If you understand it, let me know. Yeah, that's good. Nestor Alema, I'm glad to have you here and I hope you're enjoying the class. Hi, outside. We are glad to have you here. Let's just progress, guys. We still have a lot to talk about. Now, this is for basically reflection and how it works. Now, there's something I want to show you guys. Observe something. The angle that this guy is making and the angle that this guy is making. Can we see that something is kind of similar there? This thing looks like a right angle. I don't know if you have seen that. Yeah. And before we even talk about that, there's something I want to point out. Observe something. This one is very more important. Under the laws of reflection, there's something you should take note of. The angle here for theta I and the angle here for theta arrow are the same. So one of the key laws for reflection, like we know, is that theta I must be equals to theta arrow. Okay? It is a law for reflection. So I will just put it in this box and add law of reflection. It must hold constant. Now there is another law of reflection that we know. I hope we are following. I think this place is very better, so I won't be causing shadow on the, what they call it, the board. This is actually part of it. Shadow and the rest, they are part of optics. So I just remember these things as we progress. You can remind me in the comment section to talk about shadow, okay? So that I won't forget. It's for your own good. Now this is one of the law of reflection. It states that the angle of incidence must be equal to the angle of reflection. Okay? And that is what we have here. Now there's another law of reflection, in case you are taking notes, which is very advisable, that states that the angle of reflection, the angle of incidence, or well, let me say angle of incidence. What do we call this? Incident ray. Let's use what we actually see here. The incident ray, normal, and the reflected ray must act on the plane surface. Must act on the surface of the plane that they are incident to. What am I saying? You shouldn't be having something like this, and this one is being reflected off another surface. That is, the theory guys must be acting on the plane of the mirror. Okay? But the most important law we are going to be working with is basically this. such that if you were told in a question the angle of incidence of a light ray on a mirror surface is 40 degrees to the normal. 40 degrees to the normal. Let's write, because most of the times I want you to be seeing what I'm saying. If in a question you were told that the angle of incidence is equals to 40 degrees to the normal, and the question was not like, let's just call it question, and the question was not like, calculate the angle of reflection, that is theta arrow, or simply arrow. How do you do this? Very, very easy. Before I solve this question, let me check if we have any questions in our comment section, because I don't want to leave anything unturned. Okay, somebody is asking a very important question. Does it need to be, what they call it, 90 degrees? You're talking about the angle between theta I and theta arrow. Most of the times, it doesn't have to be that, okay? But I think for most calculations that I've kind of checked out, there's a pattern. But don't take that as a standard, okay? The person that is asking now, it doesn't have to be 90 degrees. But one thing is true. The angle of incidence and the angle of refraction must be the same. Yes, that's it. The normal must always split the two angles into equal parts. So if it's 40 degrees for the incidence, it should also be 40 degrees for the reflection. I hope you are cleared on that. I hope you are cleared. So let's progress. That was a good question. So if this is the question, the angle of incidence on a plane mirror is 40 degrees. Sorry. Oops. That's my bad. Let's say this is the mirror surface. And then this is the initial ray acting on this surface. And like I said, this angle, 40 degrees to the normal. It means we have to draw our imaginary normal. This imaginary vertical line. That 40 degrees, we will put it in between here. 40 degrees. This is our incident angle. Now, like we know, when a light ray hits a surface, it kind of rebounds off it. Is it not? Now, we are asked to find this, which is our theta arrow, or simply arrow. Now, we don't have to do any magic. We've already know from the law of reflection that states that theta I is always equals to theta arrow. Therefore means that if theta I is equals to what? 40 degrees, because of this statement, theta arrow itself must also be what? 40 degrees. So sometimes you notice that when professors are solving this very thing, they've already seen the answer before they actually solve. So they just pick it. Okay? It's very easy. That's why it's good for you to know your laws in physics. So when I see this kind of question, I already know that because theta I is equal to theta arrow, my answer will be what? 40 degrees. I hope this is clear to us. I hope it's clear to us. Okay, the question is, does light reflect always or is absorbed? Now, that stuff I wrote there was trying to show that normally, like we know, when light is incident on a surface, okay, it gets reflected. But I'm now introducing something that is very important, that in terms of energy, it is not all the energy that was incident that gets reflected. A small amount of it gets absorbed. I hope that is clear. Okay, your next question is, can incident angle be greater than 45? Yes, it can. They can say 60 degrees to the normal. It's still correct. Okay, it's still okay. I hope this solves your question. So we progress. That was a good one. Now we know this, we'll be moving on to something very important. Still much about reflection. Observe something. Let's clean this off. Let's progress. No time to waste. Alright, look at something here. there is something under reflection, under this very aspect of reflection we have to know. It is called glancing angle. Okay? Glancing angle. Now this guy is not an angle between the incident ray and the normal. Like saying it has nothing to do with the normal. But this time around, it has to do with the plane of the mirror itself. So if you are talking about glancing angle, this is where it is located. Assuming this is the mirror surface. This is the mirror surface. And then light ray gets incident on it. Like we all know, this. The glancing angle is the angle between the incident ray, don't worry, I'll write this one out, and the plane of the mirror. So this is the glancing angle. So if I was to write it out, what is glancing angle? What is glancing angle? You can tell me in the comment section, what do you think will be my definition for glancing angle? Let me see if somebody's able to get it. What do you think would be a good definition for glancing angle? What do you think would be a good definition for glancing angle based on what I've already explained? Anybody? Who's got an idea here? If you are new to the channel, I would love if you actually join the space. I am free most of the time. Saturday, I should be doing videos that should be of help to you guys. So just do it to stay tuned by subscribing. Alright, so let's give it a definition without wasting time. Glancing angle is the angle between the incident ray and the plane of the mirror. Alright, so this should be a good definition for glancing angle. Now, why is this important? It has relevance in relation to reflection. Sometimes it will be like, calculate the angle of incidence. If the glancing angle is given as, let's say, 50 degrees, what would be the angle of, what they call it, incidence? That's some question you have to know how to solve. So that's basically what we'll be explaining here. And we'll use that question as our starter. Okay? We are going to be using that question to start glancing angle. We have to use it to start it better. Alright, let's see what glancing angle will look like. We've already said it's the angle between the incident ray and the plane of the mirror. So that should be at the back of our mind. So if a question was like saying, alright, let's see what this question is saying. Calculate the angle of incidence given that the glancing angle is 50 degrees. So this is our question. Before I continue, let me check if anybody's got any question for me. So somebody is asking, entering glancing angle will be equal to the reflection glancing angle. Yes, very good. That's very, very correct. Very, very correct. I like your question. This is it. So he's saying that the glancing angle here is equals to the glancing angle here. And I'm saying yes. Very, very true. And what is the, should I say, my analogy behind it? What is my reason? We call this our normal, right? N. Now we said that here, whatever is here, which is I, incident angle, is equal to what is here, which is R, reflected angle. So if what is here is what is here, okay, it means that if this is angle 90, you remove, let's say yes, let's say 60 degree. We know this is angle 90. From here to here is angle 90. And from here to here is also what? Angle 90. If here is 60 degree, you remove 60 from 90, what will be your glancing angle? 30 degrees. And based on the rule or the law of reflection, we said that angle of incidence must be equal to what? Angle of reflection. It means that here will also be what? 60 degrees. This is bad. Let's do a change. Must be equal to what? 60 degrees. I must be equal to R. And this is also a right angle. So we will remove 60 from 90 degrees. What will be left also? 30 degrees. So that will be true. That will be true. Okay? Now this is the next question. They said, if light is incident, okay, if light is wave form of energy, why draw straight lines? Okay, this very question is very tactical. They said, if light is wave, why draw straight line? Basically, when you are doing ray diagrams or optics, you basically use straight lines, okay, for geometry purpose. We just work with straight lines. But we know that light can occur as a wave. We are going to give you the property for that. But in optics, the part that has to do with the diagrams aspect, you can check your physics textbook and all that. We basically just work with straight lines. Imagine I'm drawing something like this, and then put the angle of incidence. It will kind of look weird. I don't know if you get. So just to make everything look more cleaner, we work with straight lines. But we know that what? Light is a wave, and it's not just a wave, it's an electromagnetic wave. We'll definitely get to that. I hope you are clear. Hi, Ricky Blocks. We are glad to have you here. Alright, let's continue. Let's continue. This is the question. Calculate the angle of incidence given that the glancing angle is 50 degrees. So let's see how this will look. Let's see how this will look. We'll draw a line. Then this is our incident ray. And then this is where the glancing angle is. They told us that it is 50 degrees. So I'll write that out first. Now we know that there will be an imaginary number, always vertical. And because of the law of reflection, this guy will bounce off the surface. Is it not? Now, we are asked to get I, which is here. How do you think we are going to get it? It's very easy. We must note that this is a right angle. Between here and here is a right angle. And right angle is always equal to what? 90 degrees. So the sum of these two angles will be equal to what? 90 degrees. So what is the first angle we have here? 50 degrees added to I must be equal to what? 90 degrees. Good. 90 degrees. So what do? We are looking for I basically, our angle of incidence. So we will just simply make I the subject of this very equation. How do we do that? Watch out. Here is 50. We don't need 50 on this side. So we'll make it cross the equality sign to this side. What will be left? I will be left. I will now be equal to, mind you, there is 90 here. So I'll write that first. 90 degrees minus, why am I saying minus? When 50 crosses the equality sign, it becomes negative 50 degrees. And if you do that simple subtraction, we get what? 40 degrees as our angle of incidence. I know for some of you, you can just simply do this with your eye very fast. And that is if and only if you thoroughly understand this, that glancing angle is the angle between the plane of the mirror and the incident, what they call it, the incident ray, and that glancing angle plus incident angle is equals to 90 degrees. Okay, this would help. So you can just know in your eye that 90 minus 50 is what? 40. You are good to go. So we are making good progress. We are making good progress. I hope you understand up to this very point. I hope you understand up to this very point. Alright, somebody is asking, does gravity affect light? I can't really say for sure. Okay, wait. You said because we say normal is what? Plumb. Does gravity affect light? Gravity affects basically anything that has mass. So except we're not saying light has mass in a sense, though it will be very, very small. We can't say light are, should I say, electrons or subatomic particles. So you're saying, so we assuming that gravity will affect it might not be necessary. And I don't think that will actually be possible. I know it does when you're talking about black holes and the rest, but let's not go into things that are complex. Let's just keep it straight for the now, okay? Let's keep things straight. So let's continue. Let's see something here. We've already studied glancing angle, and I hope you understand how these guys work. Okay? Let's simply go to what they call it. Refraction. I hope you've already, should I say, go through this. If you're the type that do screenshots, do give it a screenshot, that will be better. So I'll just count 1 to 5, you screenshot, then I clean the board. So you are free to screenshot if you're the type that want to screenshot. So we can progress, right? Yeah, we'll do that right away. So I suppose we are done screenshotting, right? Let's continue. We will have to finish so many things today, and I'll just be, for today, a bit detailed and all that. But also revise it up to wave equation. Let's see if that is very much possible. All right. I hope we are understanding what we are doing basically. So we'll just talk on refraction. All right. We'll talk on refraction. God helping us. Let's see if we have any questions. You are welcome, Nesta. Thanks for staying up to this very point. All right, we progress. For those of you that are just coming, I'm glad to have you on this space. If you are new to the channel, do it to drop a follow so that as we progress or in subsequent live session, you'll be duly notified. All right? So we'll progress right away. Now let's see something here. We all know that light wave can travel through any medium because itself is a wave. And like we said for waves, they have the ability to what? Pass through mediums. If you check that definition, you see that I kind of underline medium. Is it not? That is, a wave can pass through a medium. So light wave can pass through medium. And because they can pass through medium, there's a property we must study. And that brings us to refraction. What is refraction? Refraction, mind you, I am not kind of sticking headlong to any known definition, I'm just talking things based on how I understand it. And I think it's a good starter. I don't cram things. We just talk it the way we know it. And God helping us, we are good to go. Refraction is the bending. Okay? Now, because we are talking about optics generally, we'll be saying of light, not of waves. We are just restricting everything to light. Okay? It's the bending of light. You can just say wave if you care, as it passes, alright, let me make this better, passes from one medium to another. So what happens during refraction? We have to know that. But before that, I will advise you go through the definition again. Refraction is the bending of light as it passes from one medium to another. Now, assuming this is what we have. This is air, and this is water. So this is plain air, and then let's just do it like this. This is water. Kind of make it rectangular, kind of, so I can be seen the difference. Now this is open air. Okay, light rays was coming in this direction, incident on, what will I call it now? The surface of the water at an angle with an imaginary normal. So we call this our incident ray. Incident ray. Okay, let's just write it in full. Incident ray. hitting the surface of the water. I hope you understand up to that. I hope you understand up to that. Now, if this is true, guys, an incident ray is impending on the surface of another medium. Mind you, this is air, this is water. There are two different mediums entirely. Now, what this law, refraction is talking about is that as waves generally passes from one medium to another, they tend to experience this bending either towards the normal or away from the normal. Take note, there are two scenarios that can occur. The wave can either bend towards the normal or away from the normal. I will tell you the conditions these are dependent on. Now this wave, let's just extend the normal downward. Okay? Now because we know that air is very much less denser than water, this guy is thicker than this one. So what will happen is that this light ray will not be able to travel as fast as it would in air because it's about entering into another medium. Now because its speed has kind of been reduced, I will also tell you what will also be reduced. There are other things that will be reduced. What will now happen is that you now notice that this guy will actually bend towards the normal. Are we seeing that? It will bend towards the normal. So it will continue like this. Okay? We know that the angle between the incident ray and the normal is always what? The incident angle. Perfect. Now, this guy has passed through this medium. It has bent kind of towards the normal. Now, why is this happening? That is what reflects. These guys are two different mediums. Now, because of that, the light ray will not travel as fast as it would in air, because this is going to be a different medium. Now, take note, asterisk and write that during refraction, okay, there are a number of things that change. One, there is a change. There is, all right, change in velocity, which we know to be what? Speed. So take note, that is one of the things that happen during refraction. The speed in air will not be the same as in water. Let's kind of make this water-like. The speed in air will not be the same as in water. What else will change? There will be a change in wavelength. Wavelength is represented or given as what? Lambda. This is the sign for reference purpose. There will be a change in wavelength, and in this case, velocity is what? V. Are we together? I'm just talking about the basis of everything. Before that, let me check if we have any question. Let me check. Okay, somebody is saying that during refraction, it will always bend towards the normal. Okay, I don't think that is true, and I'll tell you why. I have seen the question now, but let me just finish, then I'll give you reasons for what I think. Now let's continue. During refraction, there will be a change in velocity. First thing first. During refraction, there will be a change in wavelength. During refraction, the frequency remains the same. Take note of this very fact. That is to say, wavelength will change, velocity will change, but the frequency will not change. And there are questions like that if you are taking school exam and external exams, okay, university preparatory exams. They will be like, which of the following parameter of a wave does not change during refraction? The answer to that question is frequency. It's frequency. It does not change. Take note of all these facts. It does not change, but rather it remains the same. Okay? Now we continue. If we have known all this, let's now get back to something. This is air, this is water. Like I said, we know this is less dense. I'm getting back to that person that asked a question about it's always bent towards the normal and all that. That's what I'm getting back to. So ensure you stay put. Now we know that this is more dense. Let's see if we can squat this somewhere. Now, like I said, if let me check something. I'm coming, guys. It doesn't change. You can check it out. You can check it out. It doesn't change. It's only wavelength and what do you call it, velocity that change. You have a Google. You can check it out. All right. All right. Let's continue. Now, let's do this. I think I will have to expand this so I can accommodate. I don't want to kind of manage anything. Take note. Asterisk and right also. If the light ray is coming from a less dense medium, so a more dense medium. Let's continue. If it's coming from less dense medium, so more dense medium, the scenario will be different from when it is coming from a more dense medium so a less dense medium. Let's just stay close together. We are almost done with this part. So let's see what happened. Now, if the light ray was coming, as we are seeing in this case, from a less dense medium, which you know to be what? Air. So a more dense medium, which you know to be water. What happens is that it will what? Bend towards the normal. Take note of that. Take note of that. It bends towards the normal. Now, if it's coming from a more dense medium, so a less dense medium. So in this case, we're assuming like the ray is coming from underwater. Let's say sea divers is under this water, and it's kind of pointing its light outside of the water. Let's assume that. So the light is coming like this. Imagine somebody is down here, all right, with a torch in hand, and is pointing it towards the surface of the water. Now we know that there will be an imaginary normal also here. Just kind of manage what I'm doing now. There will be an imaginary normal. Now this incident ray will make an angle with this imaginary normal, which we call what? I. Okay? Now that is the angle of incidence. Now we know that the ray is going to pass from a more dense medium to a less dense medium. So we'll be talking about something like this. What will happen in that case? In this case, the light ray will bend away, and that answers that question, from the normal. The light ray will bend away from the normal. Emphasis on away. I hope that is clear. So this is how it will now look like. Instead of it to just continue going in this very direction that it was coming from, instead of it to just continue going like this, it will now bend furthermore away. Are you seeing that? So what will now happen is that the angle here, which we now call the angle of refraction, the angle here, which we call the angle of refraction, will be greater than the angle of incidence. I hope we are getting this thing. Whereas in this case, remember the angle here inside the medium will be the what? Angle of refraction. The one outside is the angle of incidence. So inside is what? Angle of refraction. In this very case, I think I will need to write this on a separate, but let me not be congesting things. It won't be good for us if we continue congesting stuff. I hope we understand up to this very point. I want to make sure that I want to be clear that we are following. I want to be clear that we are following. If you understand, do it to let me know. If you understand, do it to let me know so we continue. Let me check. I hope you understand up to that point. Good question. I will get to it. I have seen your question. You said, will light eventually dissipate, or that light energy is what? Transferred to the water. I'll get to that. Let me just finish explaining what I'm explaining so that I won't get everything complicated. All right, good questions. Like I said, we continue. Now, from a less dense medium to a more dense medium, I'm analyzing that. Less dense to more dense. All right? Let's see what happened. Now, if this is the scenario we are talking about, air outside is less dense. Inside the water is more dense. Now, this is an angle of incidence of the incident ray hitting the surface, and because the water is more dense, the ray will bend towards normal. Observe that it did not continue in this direction, but rather it has bent. So, for this very scenario, we can say that I is greater than arrow. Mind you, the arrow I'm talking about here is, arrow in this case is angle of refraction, not reflection. Angle of refraction. Take notes. Arrow in this case, we are talking about refraction now, is angle of what? Refraction. So this is what happens when it's going from, e.g., air to water. This is what will happen. And then not just that, what will also happen is that what? The light ray will bend what? Light ray bend towards normal. Take note of this thing. Take note of this very thing. That's what I finished analyzing. So we are good to continue. We are really good to continue. Now, what if it was going from this to this? That is, more dense medium, okay, so less dense medium. What will happen in this case? It will be different from the first case. Okay? Before we continue, let's give ourselves an example. E.g., from water to air. Now this is the case we're analyzing. Someone under the water kind of pointing torch or light rays from his torch outside. It makes an angle of incidence at this very point with the imaginary normal. Now, because it's coming out to a less dense medium, it will bend away. So it did not continue in this direction. It did not continue in this direction, but it has what? Bend. Did you see that? So what can we say? Comparing this angle to this angle, you will agree with me that what? First thing first, angle of incidence is less than angle of refraction. True or false? True. So you take note of this. And next thing next is that what? What happened here? The inverse will happen here. Light rays bends what? Away from normal. So guys, I hope you understand this. I will take your question now. I hope you understand what is on the board, guys. So we progress without wasting time. It's kind of getting blurry here. I don't know if you are seeing me. Let me just try and make it up for us to see. Let me try and make it up. Let me check again. Okay, I think this is better off now. It's kind of clearer, right? So let's continue. So let's get back to the question is asking. Will light dissipate or that light energy is transferred to the water? Now, we've already said something similar for what they call it, reflection. Let's see what will actually happen in refraction. So before I clean this part of the board, if you are the type that is snapping or taking notes, do where to take note, do where to screenshot so you can copy it if you are copying it. So we progress. Thanks for staying, guys. Thanks for staying put. We are about to continue. So let's continue. I'm wiping. So for that very question, let's see what actually happened. Like I said, if you are new to the channel and then you love to be a part of this page so that when we go live next time or some other time, you will be duly notified. Alright? And then before I forget, a very important announcement. A very, very important announcement for oops. I don't think this is good enough. Let me announcement for science students. Alright? Science students. Now, if you are a science student, I have a very good announcement for you and a good news for you. Now, if you click on, what I call it, check my profile on YouTube here, you check the bio, there is a link that has this name, Physademy. It's a WhatsApp channel link. You will see it if you actually check my bio right now. It's a WhatsApp channel. Now, if you are a science student or you know any person, let's say in your community, your class, your neighbors or the likes, family, friends, and the rest, that is a science student and you are trying to get started with chemistry, physics, biology, and English, those subjects I've just mentioned, chemistry, physics, biology, and English, I do post good content that will actually give you an edge if you are preparing for, let's say, school exam or you are planning to be writing JAM next year. Okay, you can actually get started with Physademy. There are a whole lot I'll be going right now. We have already done like 17 chapters or 17 topics in each of those subjects I just mentioned. So I actually just remember, so I just have to tell you guys, in case you are a science student and you love to be part of the family, click the link in my bio, go to my bio, then check for Physademy among the link. I think that's the only link there as of now. It's a WhatsApp channel link. Click it and join the channel, okay? There is stuff for you for today's stuff. There's even today's stuff that I did post today. And I hope you will find them very, very much helpful. Trust me for that. So this is the announcement, okay? Tell your friends, let them know that there is something called Physademy where they can get started with their preparation for any science exam. I hope this helped. So let's get back to our stuff. Sorry for the interlude, and I hope it was kind of helpful to you. Alright, let's progress. Let's make good progress. Good progress. Now, this is a medium. Let's just say this is the plane. This is a medium, let's say air, and this is water. What actually happens when light ray hits this surface? That is what we are going to be analyzing. What actually happens when light ray hits this surface? Now, we know that there's an angle here, I, angle of incidence, carrying a certain amount of energy, okay, which can call the incident energy. Now, it then hits this water surface, and we know it refracts. This is the normal, imaginary normal. Okay? It bends towards the normal. It does not continue in this, what I call it, supposed direction, but it bends towards the normal as this. I hope we are good. Now, what actually happened to the energy that the initial or the incident ray was carrying? Excuse me, let me drink water. Let me actually drink something to just calm my nerves. Kind of stressed out. Alright, we progress. Let's see what happened. Better now. Let's see what happened now. Look at this. This guy is carrying a certain amount of energy. And when it refracts, it has an angle R. Okay? And we know that as it's passing through this water, the energy will be what? Absorbed. Okay? The energy will be what? Absorbed. But there's also something that actually happened here. There's the fun fact that says that a little part of that energy is also, what do you call it? What do you call this? What do you call it? Reflected. So this is what I'm saying. This is what I'm saying, guys. Get this straight. This one is not working. For refraction, this is what happened. I think this answers your question. Incident energy will be equals to reflected energy plus absorbed energy. So I think that answers your question. That is the what I call it, the light rays that get refracted was absorbed. Why a little of it? Because light is a wave, and a wave in any condition must always obey the properties of a wave. So there must be some fraction of that wave that gets what? Reflected. This one will go off. Most of them that pass into the water will get what? Absorbed. I hope that answers your question. I hope that answers your question. So we progress without much delay. We progress. That is for that. We are just touching in general knowledge. Okay? God helping us, we will go in details. Now, let's continue. I hope that answers the question. Now look at something. I think I've basically explained what they call it. Refraction. I think that's a good one for us. Let's quickly go to diffraction, interference, and directs. Let's go to interference before we go to diffraction. Now there's a whole lot to this. I'm basically just keeping the calculation that are associated with this for the now. Let's just get a thorough knowledge of the concepts of each of these. Then we can talk about calculation, because it's concept first before calculation. Let's progress. Now interference, basically, how do you define interference? It's basically what happens when two waves are superimposed on each other. So we are not really cramming any formula. I will never do that for any class. It's basically what I've learned over time, then I will come and use it to teach you guys. Interference is what occurs whenever, I think this will not work there, whenever two or more waves are superimposed on each other. So interference basically is talking about superimposition. I hope that is clear. So let's say we have something like this. Okay, before we go into that, there are two types of interference. I don't want to miss it. Thank God I just remember. Interference can be of two types. Okay? We have two types of interference. We have the constructive, and we also have what they call the destructive. So these are the two types of what? Interference. We have constructive interference and destructive interference. So this is basically what we have for interference. Okay? Just give me a minute, let me go and get something. And just give me a minute, let me go and get something. Okay, I think there's another question. Okay, it's asking, is the energy absorbed the same as the refraction energy? In this case, we can take it to be that, because the light rays will not just continue going, or let's have it continue going downward into the medium. it will be what? Getting absorbed gradually. It is the minimal one that gets reflected that will be saved. I hope that helps you understanding. So guys, just give me 1 minute, let me go and get something, okay? 1 minute, I'll be back. Alright guys, thanks for your patience. Thank you very much for your patience. Thank you very much for your patience. Alright, let's continue. Let's explain what constructive and destructive interference is all about. Okay? I want to actually ease myself, and I think that was kind of necessary. Alright, let's continue. I'll just show you how it works. I will just show you how it works. Now let's see what constructive and destructive interference, how they work. Now this is it. Constructive interference. Just to give you a starter, we are going to look at constructive interference. So assuming you have this wave, mind you, I'm talking about light wave, basically. Now it gets superimposed on a smaller one. It has an amplitude, okay, let's call this A. Basically, that is it. Okay, sorry. Okay, this is the original wave. Now it gets superimposed on another wave. It's moving in this direction, it's progressing in this direction. Then it gets superimposed on another wave. Okay, let's say plus a smaller one in terms of amplitude, energy, and the rest. Okay, I'm just kind of sketching things out here. This one has a shorter amplitude. Are you seeing that? It has a shorter amplitude. Now, we will call this guy, because it's bigger, we'll call it A1, and we'll call this A2 in terms of amplitude. Now, if these two guys that are traveling in the same direction superimpose on each other, I think in textbook they'll do something like this, coming in this direction, coming in this direction. This is the first wave, and this is the second light wave. Light, most especially, we are talking about optics. Now, when they get superimposed, what happens is that the result will be equals to, watch out, this will be the result. The amplitude of this guy will be added to the amplitude of this guy. Why? Because the energy of this guy will be summated with the energy of this guy. Okay? So imagine a wave that is formed, that will now be formed of a higher energy. And because of a higher energy, it will have a higher amplitude. Okay? Because basically the higher the energy, the higher the, to some extent, it affects the amplitude of the wave. But most essentially, it affects what? The wavelength of the wave itself. But let's just get things straight here. How will it now look if this and this superimpose on each other? It will become something like this. And I think this works, kind of work. Alright, let's get this straight. Now if you check, there will be a new amplitude here. Okay? There will be a new amplitude. A. Now this new amplitude, A, is equals to A1 plus A2. Get that straight. Get that straight. They were of different amplitude and different energy. Now this wave was carrying energy 1, this one was carrying energy 2. For the resultant, the final E, let's just call it A final and E final. A final and E. Why will I call it A? Will you understand? Okay, let's just say where A is equals amplitude, E is equals energy. E final will be equals to what? E1 plus E2. I hope that is clear to us. I hope that is clear to us. All right. Okay, he's saying that seems light wave affects, what do you call it? Gravity affects light. I don't think it's in terms of that. The what do you call it? What actually, if you ask me, that caused the bending of the light ray as it passed from a less dense medium to a more dense medium. If you look at it critically, in the less dense medium, the molecules that make up the medium are less compacted. There's kind of enough space. So the light ray kind of receive less bumping into molecules. So it just kind of go into a more smoother course. It go along a more smoother course. But when you enter a more dense medium, because the molecules are kind of closely attached to each other, they kind of cause this bending. I don't know if you get me. Because it bumps into them, and as it's bumping into them, it's losing energy, right? And as it loses energy, you don't expect it to go away from the normal. That bending towards normal is showing that it's actually losing energy. So the molecules of the medium. So that's what causes the bending towards the normal, not necessarily gravity. I hope that is clear. All right, what's the next question? Okay, that's good, that's good. So we continue. So this is what happened under constructive. I just want to dedicate this board. So basically, constructive interference, this part of the board, I mean. So observe something. For constructive interference, the wave must be moving what? In the same direction. That's only when it can be constructive. So like saying before superimposition, the wave must be what? Direction. So let's write that down. I think that would be a good one. And B, the waves, because I can't say, okay, let me just say the two waves, but you know it can be more than two, right? The two waves must be moving in the same direction. Guys, if you are just joining now, I would love if you actually subscribe to the channel. That is, if you want to be part of the classes that we follow, so that you don't miss it. Okay, it's very important you stay put. So if you find the content the class of today very, very helpful, it will be good if you actually subscribe, so that you won't be missing classes. Okay, you won't be missing subsequent classes. The two waves must be in the what? Moving in the same direction. That is only when it can be what? Constructive interference. I hope we are going to clean this part of the board. Let's clean it and continue. So whatever we are talking about now is about wave, and wave in relation to what? Light. Because light itself is a wave. So we are analyzing everything we need to know about how light wave works. How it undergoes reflection, refraction, and direct. That's what we are analyzing, guys. Okay? For now, we are just keeping anything calculation related by the side, so that we don't overcomplicate things for ourselves. So let's see destructive interference. I hope the network is still working. Let me check. I just want to be sure it's not breaking over there. If you are just coming, I'm glad to have you on this space. Very much glad to have you. So let's continue. Don't forget to like and share to your friends. To go a long way to get them understand light waves. Now let's continue. Destructive interference. Now you have a wave. Alright, let me make this kind of bigger. Okay. Alright, oops. Right back. You have this wave. Okay. Now it has an amplitude A1. Alright. Then you have a smaller wave. Okay, it's moving in this direction, but direction must be specified. is moving in this direction. Take note of the direction is moving towards the what? The right. It's going towards the right. Are you seeing that? Then what else do you have? A second wave. Okay. This is the second wave, or let me just make it kind of a bit smaller. Sorry for the diagrammatic inconvenience. A2, A1. Okay, I can actually make this better. I can actually make this better so that I won't be straining your eyes. I can actually make this better. Let's call this A2. Now we know based on observation, and it's moving in this direction. Observe the direction differences. Are you seeing that? So this is the wave, and they are moving in opposite direction. Now what happens if they happens to supersede each other? This one was coming in this direction of a larger amplitude and a larger energy, A1. And then it's superimposed on a wave that is traveling in the opposite direction. Okay? Now this one is going like this, A2, A2. Larger amplitude for A1. Are you seeing that? So what will happen is that, okay, let's write the criteria for destructive interference. For destructive interference, what do you think? Will it be the same condition as this, or it will be the opposite? Let's see what will happen. The two waves, the condition is that the two waves must be moving in the opposite direction. So this is the condition, guys. They cannot be two waves moving in the same direction and you expect destructive interference to occur. It's not possible. The two waves must be moving what? In opposite direction. That is only when destructive interference can occur. I hope that is clear to us. So let's basically see what will happen from here. Because the two waves are moving in opposite direction, okay? What will happen to the amplitude and what will happen to the energy? We have to see that. Now, observe something. A wave is trying to go in this direction. Another wave is trying to go in this direction. In the name of superimposition, what do you think? It's like you trying to run on a very, very rough floor, okay? Or trying to push a bucket or a box across a very, very rough floor. You notice that the movement will be slower than when you are moving that same box on a smoother floor. True or false? True. So, assuming this oppositely directed force or wave, assuming this oppositely directed wave is what? A frictional wave. Just picture it in terms of friction. What do you think it will do? It will kind of dissipate the energy of the wave going in this direction. So we'll now have something like this. Final amplitude of the wave will now be A1 minus A2. Okay? Some part of this guy will go in order to overcome this oppositely directed wave. The leftover will now be what will move the wave in this direction. So going in this way, experiencing what? An opposing, going in this way, experiencing an opposing, wave. Some part of it is lost in order to overcome this wave. The leftover pushes it downward. So this is how to now look. It will now have a lesser amplitude. Reason being that it has what? Use some parts to overcome the oppositely directed light wave. So A final will kind of be equals to A1 minus A2. Take note. Now because the energy of this wave was moving in this direction, but the energy of the opposing wave was moving in this direction, some of the energy of the wave that was moving in this place will be used to overcome the opposing wave. The leftover will now move the wave in this direction. So the final energy will be equals to E1 minus E2. So this is for destructive interference. So take note of this. Take note of this. It's very, very, very much easy. And I hope we clearly understand how it works. I hope we clearly understand how it works. Are we good? So now we know something about interference. We'll be saving ourselves a whole lot of time by going straight to what? Diffraction. Diffraction. Okay? Diffraction, here we come. Let's see what we have to know about diffraction. I'll be treating it side by side with polarization to save time, to save time, to save time. Alright, we progress. We are talking about the next thing, which is diffraction. Diffraction. That's what we are talking about now. Now, when you are asked what diffraction is, what will you say? What will you say? Hope we are still good to continue, guys. I hope we are still good to. All right, diffraction is the ability of a wave to bend around obstacles in its path. That is diffraction. That is what? Diffraction. I hope we are good. That is diffraction. Okay? Now, I will just go straight and illustrate, what do they call it? How light can be diffracted using a glass prism. I will explain diffraction using a glass prism. Now, this is a glass prism, usually triangular. Okay? We are viewing one side of it. Okay? Normally, it's a three-dimensional object like this and the rest. Okay? But basically, okay, I think this should be better off. Right? Okay, let me just remove this side and make it two-dimensional so that we can progress without much more delay. So imagine light ray was coming from this direction. Light ray, okay, coming like this. Light rays coming like this. Light rays coming like this. Now, as it passed through this guy, the glass prism has its own what? Density, different from that of air. Let me add the name. This is not. Let me check the other. The glass prism has its own density. This is air, and this is the glass prism. The glass prism has its own density, different from that of what? Air. So as it passes through this guy, first and foremost, like we know, let's not deceive ourselves, it will be what? Refracted inside the medium. You see not? Because this is more dense, there will be a change in direction. This one that is here will come this way. Okay, let me not make it too obvious like that. Just take it this way. This one will come this way. This one will come this way. This one will come this way. That's basically what will happen. Okay? Now, when this guy start coming out, because of the power of this guy to actually diffract the light rays, they will spread out into spectrum. What do I say? Spectrum, light spectrum, light spectrum. Okay? This experiment was actually first carried out by Isaac Newton. Okay? To show that light is made up of a spectrum of other waves. Okay? He was the one that first diffracted light wave. So the light ray that was here initially, we spread out into what? Spectrum on this side. And that is what basically happened for light waves. Sorry for the brief delay. Alright, let's continue. So how will the spectrum look like? Where's my pen? Now we know when we are talking about spectrum of light, let's just write it here, light spectrum. We have to know how the spectrum will look like. It will spread into spectrum, what we call colors. Let's just say colors. It's trying to say that light is light wave or white light. I think that will be better here. That will be better here. Sorry for the what do you call it? Inconvenience. That will be better here. White light. It spreads out into spectrum in the name of trying to get diffracted. Okay? Now let's see how the spectrum will look like. There's what they call light spectrum. Okay? Now, when light gets diffracted, it spreads into a set of other waves that actually join together to form white light. Okay? We know that it will be ROY. I think I should write it vertically, better off, to make things easy for us.